All right, thank you very much for being here. We're so pleased to have Thad Domina either way, with us today. Thad made the long trip all the way up from Irvine. He is a newly minted associate professor at the UC Irvine School of Education. Thad uses both demographic and econometric methods to answer questions about that are informed by sociological theory. His primary interest is in student transitions from middle and high school to college, and in particular questions about how the sorting processes affect life chances, and about identifying educational strategies that can expand opportunities for all students. Thad received his PhD in sociology from CUNY in 2006 and did a postdoc at Princeton. He's been published in many great journals in both education and sociology, and we're delighted to have him here today.
So that's the first time I've been introduced as an associate professor, which is really nice. So it put me in a good mood. The fact that you're all eating and I'm not puts me in a bad mood, but to balance out. So I've got a lot to present and not a lot of time. I'm going to try to keep an eye on things, and I'm also going to be mindful of the fact that you're all really comfortable and try not to be too boring and put you to sleep. You're going to be comfortable and well fed, which is dangerous. So I'm going to tell you about some work that I've been doing about accelerating middle school math, which has become sort of an obsession of mine. It's a really sticky question, and maybe I don't need to say much more than that because the stickiness becomes apparent pretty quickly. And so I'll start with sort of an obligatory slide that compares U.S. high school students with their peers internationally. And we all know that U.S. high schoolers don't do as well as we'd like. They don't do as well in math as they like. They do particularly poorly on problems that are conceptual, that require application. The sorts of problems that one is typically first exposed to in algebra. Now, we also know, I know via Morgan, that in the U.S. We expose kids to algebra a couple years later than these OECD countries that we are comparing ourselves against when we do these international comparisons. So, the thought, which is pretty widely held, is that we ought to change our math curriculum. We ought to expose kids to algebra earlier and more intensively. And by doing so, we hope to narrow this achievement gap between us and the rest of the world. Currently, the hope is that the Common Core is going to help with this, right? It's going to standardize our curricula from K all the way through. It's going to make sure that kids get algebra starting in 8th grade and through to 9th grade. Before the Common Core came along, and not unrelated to the Common Core, there's been this push just to change course enrollment patterns. And the most sort of, this push happens at the end of middle school typically, and the idea is to put kids on a track in middle school so that they can progress through a math curriculum to calculus by the time they graduate from high school. So the way this happens, and the way we often talk about this, is in terms of 8th grade algebra. And so what I've got here are some numbers from NAEP that track 8th grade algebra enrollment trends for the US in red and for California in blue. Don't take these numbers so very, very seriously. NAEP asks kids to report their 8th grade math class, and kids aren't the most reliable narrators. They also, the questions change ever so slightly from year to year, but there's enough continuity across the questions and over the time to believe pretty strongly that there's this really pronounced trend in 8th grade math enrollment, from around 15% in the early 90s to around 35% nationwide today. In California, it's closer to 60%. We've changed middle school math curricula, intensified middle school math curricula. We've, in many cases, eliminated choice for students. Kids, along with their parents, along with their counselors, used to decide, do I take grade level math, do I take pre-algebra, do I take algebra? Lots of schools have just tried to lop off the bottom of that choice set and push more and more kids into the more rigorous and more challenging 8th grade algebra class. One thing we know about this push, one thing I know about this push, and I think we can be pretty confident about, is that it's worked to get more kids through a more rigorous math curriculum. So I did a paper, these numbers come from a paper that I and a grad student of mine published a year ago or so, that compares high school graduates in 82, 92, and 2004, asks what's the highest math course these kids completed credits in. And what you can see is that in the class of 82, nearly half of kids in the national high school graduating class of 1982 didn't get beyond algebra when they got their diploma. That number shrunk dramatically over the last few cohorts, over the last few decades. And these days, about 15% of high school graduates graduate, get a diploma with just algebra or less advanced math. And at the top of the continuum, you can see that there's also been a huge expansion in fancy math class taking. That's a technical term. You've got about 3% of kids taking algebra in the class, taking calculus, graduating with calculus in the class of 82, blows up to about 15% in the class of 2004. So we've pushed kids at the beginning of this this sort of structured math curriculum, and we're getting kids through it. This is good news. We're also mitigating the sorts of inequalities that have marked this math sequence. So black-white inequality in highest math completion was far wider in 82 than it was in 2004. Class-based inequality in highest math completion was far wider in 82 than it was in 2004.
You have graphs to show that.
What?
Yeah.
I'm not going to show it to you today. And it's an interesting story. So this paper, it's an AERJ paper from 2012, asks exactly that. And it's an interesting and somewhat more complicated story that I'm giving you because at the very top of this distribution, in calculus completion, those inequalities persisted. But in pre-calc, in trigonometry, there we've seen dramatic narrowing in inequality. Gender-based inequalities have flipped, by the way, but that's a whole different story. So we're getting the kids through. We're making some progress. We're making some headway in getting the kids through a structured math curriculum. But that's not the same thing at all as helping kids learn math. And so what I'm going to ask you about today are about the effects of accelerating middle school math on student achievement. I came to this work sort of informed by a sociological perspective. There's a long literature in sociology about tracking, and in education we tend to talk about it in terms of the opportunity to learn. And it's the most intuitive idea in the world. Basically, the idea is that if you give kids challenging, rigorous coursework, they're going to learn more, right? And there's strong evidence to support this view. There's correlational work, and I'm being a little bit falsely modest when I describe it as correlational work. A lot of work that uses propensity score matching and sort of regression techniques that demonstrate that if you put kids into fancier math classes, they learn more. And there's a very little bit of experimental evidence to this regard. So the paper I've cited here, this Heppen paper, is an experiment where high-skill kids, so high-achieving 8th graders in rural New England schools that didn't offer 8th grade algebra, are randomly placed into an online algebra curriculum, and a control group's randomly placed into their regular pre-algebra class. And in that experiment, you've got evidence of a good, strong, like a 0.39 effect size, positive effect on kids learning by getting high-achieving kids into 8th grade algebra. This evidence, this literature dovetails nicely with a very strong body of work on tracking. And the idea, the evidence in tracking, the sort of consensus view about tracking, is that when you track kids, if you put some kids into a fancy math class and some kids into a less fancy class, you widen existing inequalities, right? The kids on the top move ahead, the kids on the bottom fall behind. And so what we're doing when we try to push more kids into 8th grade algebra, when we try to reduce the choice set for kids and say, general math's not available to you, remedial math's not available to you, you're going to take 8th grade algebra, what we're doing is we're trying to constrain middle school math curriculum, right? We're trying to reduce these choices down to a few choices in very rigorous courses. And this builds on work by Valerie Lee and others, which clearly argues as a school-level reform strategy, constrained curricula ought to be effective. It ought to raise average levels of achievement and not narrow inequality. So this is my sort of theoretical prior. But I come to it with also some worries, because when, at a large scale, as a matter of policy, we've tried to constrain curricula, we've tried to push all kids into more rigorous courses, we've often found results that aren't nearly as encouraging as we'd like. So I'm describing this as mixed results. There's a set of studies that were published in Teachers College Record in 2006 and 2008 describing one high school in Long Island, Burris et al., where math and English curricula were detracked. Everybody's put into a rigorous class. This is a best case scenario. Every teacher's on board. There's huge amounts of professional development. The curriculum's innovative and rigorous, and students are doing really well. There's no direct measure of student achievement here. No measure that's available for everybody, but really encouraging results out of the Long Island example. Larger scale examples are less encouraging. Chicago did something that's very closely related to the sort of thing I'm going to talk about today in 9th grade. They put everybody into 9th grade algebra and 9th grade college prep reading, or ELA. And the evidence out of Chicago, there are tons of studies looking at sort of slicing it a little bit differently, but the sort of broad strokes evidence out of Chicago is no effect on average, negative effect for high achieving students. California, I'm going to tell you a bit about what we're doing in California, but California went through a push, we're kind of at the tail end of a push to get every 8th grader in algebra. And the evidence from California is similarly discouraging. My colleagues and I have a couple of papers that look at one district that went whole hog on this 8th grade algebra for everybody kick, and the evidence that we find in this district is of negative effects on student achievement. It's not the most compelling evidence in the world because it's one district. But Liang and colleagues up in Sacramento and Davis have similar findings in California. They compare kids who took 8th grade algebra and failed with kids who took algebra for the first time in 9th grade. And what they find is that the 8th grade algebra failures are worse off than first-time 9th grade takers. And so their argument is pushing those kids into 8th grade algebra didn't work. The last piece of evidence comes out of North Carolina. Charlotte-Mecklenburg and a handful of other North Carolina school districts are doing the same thing we're talking about, pushing more and more kids into 8th grade algebra. And Huffholder and all in a series of analyses that are way too complicated, just way too complicated, period, argue or find that the average effect of 8th grade algebra is negative, and the effect is that average negative effect is particularly pronounced at the bottom of the skills distribution.
A clarification question. For the kids that get pushed into 8th grade algebra, what are they doing in math? Like, what is the sequence before?
That's a good question. Thank you. So in California and in most places, there's a menu of math options that goes something like this: grade level math, pre-algebra, algebra, geometry. So one thing that's happened over time is that pre-algebra and grade level math have sort of separated out. I'm not going to worry about that today. It's an interesting question. And in California, we tend to lump the two together because kids who take pre-algebra and grade level math take the same CST at the end of the course. So that's and Morgan can tell us more about what the content of those classes is.
Well, so that was my question: was to what extent are you convinced by arguments like, well, when they add more kids to high school algebra, they just water down what?
Yeah, I think this is important. So this is a nice transition. I'm not going to answer that question directly right now, but I'm going to use it to try to explain what I'm doing today. I think that you've got two different questions going on. The first is that you call a partial equilibrium question. It's a question about an individual kid, right? If you've got one kid who's on the margin, and you've got a choice. Do I put this kid into algebra, or do I put them into grade level math? What's the effect on that kid? And then you kind of generalize from that kid, right? What's the average effect of moving a kid from one class to another, right? That's an interesting question, but it's not nearly as interesting as this general equilibrium question, and that is when we do this as a matter of policy across the board. Maybe you should spend a second just sort of trying to make that distinction a little bit clearer. Think about class size, right? Great experimental evidence that being in a small elementary school class has positive effects on kids' achievement, right? That's what the Tennessee data shows. Good news for small class sizes, right? Partial equilibrium effect with small class sizes. And if you paid attention to California school policy a generation ago, when we decided to do that as a matter of policy, it was a little bit of a disaster. It was a little bit of a disaster because it's hard to staff a lot of classrooms with qualified teachers, right? So when you make smaller class sizes, you get less qualified teachers on the whole, and you might have a negative effect across the board, right? This is the sort of question that we're going to ask about 8th grade algebra. First, for an individual kid who moves from a less fancy class to a fancier class, and then secondly, what happens when you do this systematically, right? And you move lots of kids across a whole school, across a whole district, or a whole state, from less fancy to not fancy. And the reason that Morgan's question is an important transition to this distinction is because the assumption is when we put more kids into algebra, that algebra is going to remain algebra, right? And there's a big worry that that's not the case. Right? The teachers teach to the perceived level of the students that they see, right? And if students have lower levels of achievement, teachers might just backfill, and it might be called algebra, but not be algebra at all. I think it's an empirical question. I hope that IES funds us so we can just start to answer it. IES or somebody. Okay, so first let's talk about this partial equilibrium question, the individual student. So go back here for a second. So I'm going to try to tell you about two studies. I'm going to try to keep an eye on time that address these two questions separately. The first one is the partial equilibrium question, the move a student from from grade level math to algebra, and what's the effect on their achievement. So to ask that question, I'm going to use data from the ECLS-K, the Early Childhood Longitudinal Study. This is an NCES study. It's a panel. It's a really nice, free, easy to get your hands on source of data. The panel starts with kindergartners in the fall of 1998. It follows up with them. Fall, spring, and kindergarten. Let's just simplify. Follows up again with them again in spring of first grade, spring of third grade, spring of fifth grade, and spring of eighth grade. So you can put kids' eighth grade math outcomes in a developmental perspective. So what I'm going to do, and importantly, at each of these waves, kids' math achievement is measured using a vertically aligned IRT scale math test. Okay. So I'm looking just at public school kids. I'm weighting them by this panel weight so that we don't worry about attrition across the board. Let's just trust it for now. And we're going to ask, between the 5th grade and 8th grade wave, what's the effect of going into fancy math versus going into less fancy math? And my definition of fancy math is based on a teacher report of kids' 8th grade algebra, or 8th grade math course. And again, there are 4 options: general math, pre-algebra, algebra, or geometry. Okay, so first I'm going to give you a little bit of descriptive data. So, descriptively, we know that there are inequalities in 8th grade math course taking. I'm giving you racial inequality, there's class-based inequality as well. In some ways, these inequalities aren't as wide as you might expect. Blacks and whites look quite a bit alike. 40% of whites are taking algebra or higher. It's like 30% of blacks, 40% of Hispanics. Asians are doing better than everybody. These inequalities are probably not all that surprising.
What's the date on this and what's the reference?
So this is our ECLS-K data.
Okay.
These are these kids I'm telling you about. So this is spring 2007. So in this data set, these descriptive inequalities in 8th grade math course taking, put 8th grade math course into a multinomial logistic regression, pile on some covariates like race and class, mom's ed, test scores, and so on. And what you find is that test score inequalities, 5th grade test score inequalities, explain basically all the descriptive inequalities in 8th grade math test taking. Good news or bad news, depending on how you think about it. But that's the story about who takes 8th grade math. Now, descriptively, what do achievement trajectories look like for kids based on their 8th grade math course sequence? So this picture just sort of thinks about kids. You know, you can sort of assume that prior to 5th grade, kids are getting more or less the same math curriculum, right? We don't differentiate. We don't explicitly differentiate elementary school math. Or the extent to which we do is a matter of debate. Once you get to middle school, you're put into separate classes, right? There's sort of a cross-class tracking. So you can sort of think about these kids as having the same line, but it's useful to think about them having different tracks, beginning from kindergarten. What you see is that all the way back at the beginning of kindergarten, the kids who are bound for algebra or bound for geometry are higher achieving. Interestingly, through elementary school, the kids who are bound for fancy math classes seem to have a little bit faster test score growth than the kids who are bound for grade level math. And for everybody, the math test score trajectory sort of flattens in a way that gives you a little bit of heartburn. This is, I think, at least in part, a function of the way math tests are measured in the ECLS-K, and particularly for these high-achieving kids, what you see is a little sort of truncation of the distribution. It's not exactly a ceiling effect. Nobody hits ceiling on this test. Literally, nobody hits ceiling on this test. But what you see is there's much less, between 5th and 8th grade, people kind of lump up. The test isn't measuring high-level skills very well. It's not differentiating among kids with high-level skills. This is a problem for this analysis. I've basically satisfied myself that I've dealt with this problem, but you get to decide whether you agree. If you look at this, if you just sort of eyeball this, this is bad news for 8th grade algebra, right? These kids are ahead, and they're no more ahead. They're ahead in 5th grade, the 8th grade algebra kids, and they're no more ahead, maybe a little bit less ahead by the time you get to 8th grade. That's not a very good way to answer this question, but it gives you some sense of what things look like descriptively. So the better way to answer this question is a series of models that look kind of bitmapped here, but you can get the general idea. I don't know how much, you can tell me how much you want to geek out about the models. Let's try to be kind of quick about it. These are all, we've got panel data, right? We've got repeated observations. So the unit of analysis in the models I'm going to present to you is the kid observation, right? Every kid has at least 4, usually 5 observations. And what you're asking is about the trajectory of kids' learning, paying particular attention to the 5th to 8th grade trajectory, net of the prior trajectory. So the first model is just a random effects model that lets kids, trajectory, so the year controls control for each of the cohorts, like for the secular trend in a series of dummy variables. You've got dummy variables for each of the 8th grade math classes. You're controlling for prior achievement. This is math, reading, and also teacher evaluations of kids' approaches to learning. And then you're controlling for things like race and class and mom's education and region and so on. Right? This is an okay model, but it doesn't take into account the possibility that there are unobserved differences between kids who are bound for fancy math class in 8th grade and kids who aren't bound for fancy math class. So I think model 2 is a better model. And basically what it does is something a little bit like that picture I just showed you. It says, let's treat kids who are bound for 8th grade algebra as kids who are on a different track than kids who are bound for 8th grade general math. And let's let their trajectories vary across the panel. And then let's ask, in particular, in between 5th and 8th grade, what happens to those kids, to the 8th grade algebra kids, compared to the 8th grade general math kids. It's a difference in difference sort of analysis within a kid, right? What's the difference between 5th and 8th grade for the algebra kid, and how does that compare to the difference between 5th and 8th grade for the general math kid? Does that make sense?
I'm sorry, I might have missed this, but the test score outcome, is it like a continuous vertically aligned scale?
Yes.
So that
yeah. So it's an IRT vertically aligned. Yeah, I didn't dwell on this, but yeah, it's we're gonna look 2 different kinds of outcomes. The first is this continuously vertically aligned IRT test score. That's so in theory your score is scaled the same way in 8th grade as it was in 5th and 3rd and so on. But we're also going to look at subscales, which are IRT predicted probabilities of having mastered particular skills. This is a way to try to get around that truncation at the top end of the distribution I was telling you about by looking at the sort of high-level skills that you would hope kids in algebra and geometry classes might
Do you
get.
see in the patterns of test taking, though, that you are seeing a ceiling effect? I mean, so it doesn't have to actually hit the ceiling, but it might be that you can't get any higher than a certain level, but it's very easy to get from point A to point B, but much harder to get from point B to point C, in which case the outputs kids are necessarily going to be doing worse no matter what you do.
Well, so the high-achieving students are going to necessarily be doing worse.
Right. But
Yes.
generally we know algebra.
The short answer is yes. So one way to, I guess I should have put this slide in. One way to do this, think about this, is you think about the distribution of test scores for, like, let's say 8th grade algebra kids in 3rd grade, and then in 5th grade and in 8th grade, and I don't have that picture handy, but in 3rd grade it's a nice bell. In 5th grade it's a nice bell that's a step further, and in 8th grade it's peaked. It's got a tail on the right, but it's pointy. So what I do, I'm the royal we, what I do is a couple of things. The first is I control for prior test score times that last wave, and prior test score squared times that last wave, so that I can kind of give kids account for where kids are in the 5th grade wave, right? that's one thing I do. That's reasonably compelling. The second thing I do is I've got these subscales. So in addition to this, in addition to the single test score, I know kids' odds of, I've got a predicted probability that kids have mastered fractions, which is very closely related to algebra. I've got a predicted probability of kids, I've got kids' predicted probability of having demonstrated proficiency in calculating area and volume. So sort of high-level stuff. These are also method-dependent variables because predicted probabilities are clustered at 0 and 1. But it gives you something. And the third thing I'm going to tell you about today, but is I ran a series of sort of Tobit models where even though I don't really have ceilings, I kind of pretended I had ceilings at different points. And the results are actually quite robust to those. But it's a very legitimate concern. I think that you've got to sort of trust that I'm. You have to trust that. I don't think I worry about ceilings in the sense that kids who go into algebra are at a higher point in the distribution in 5th grade than kids who don't go into algebra. Because I think that you can control for that with this sort of prior achievement times last wave. But I think you have to worry that the test may not capture what kids are learning in algebra and geometry classes, and that's what those second set of analysis are for. Okay, some results. All right, we're good for time too. So I'm going to give you a cleaner version if you want the full model. You can look at them later. The short answer is that there's good evidence that taking fancy math class boosts kids' achievement. This is what you see in the first model, right? The kids who take 8th grade algebra and the kids who take 8th grade geometry are scoring significantly better than kids with similar levels of prior achievement who took just general math. This is good. Model 2 is a much more rigorous test of the unique effect of 8th grade algebra because it says let's control for the possibility that kids on the 8th grade algebra track are different on a wide range of unobservables. And so let's ask about how they do. Let's control for their differences before 5th grade by netting out that track, and then just ask what happens between 5th and 8th grade. What's unique about the trajectory between 5th and 8th grade? And what you get is a much more conservative estimate, but it's still a positive effect of 8th grade algebra, and it looks like a positive effect, not very well estimated, of 8th grade geometry. So you've got kids who take 8th grade algebra doing about a 1/10 of a standard deviation than they might have done had they taken 8th grade general math. This is good news. The third model, so we got sidetracked by these discussions of ceilings, so I didn't get to tell you about the third and fourth model. But the third model says, okay, well, maybe this is not about the class that kids are taking. Maybe it's about the schools that kids go to. Maybe the kids who take 8th grade algebra are going to schools with better academic climates more generally. So I just put a set of school level fixed effects models on the third school level fixed effects into the third model. And the results I get are totally consistent. So it doesn't seem like that school is explaining these 8th grade algebra effects. It really does seem like it's within school. Kids who take fancy math have a sort of bump up in achievement between 5th and 8th grade compared to kids who take less fancy math. So the fourth model sort of has the same set of ideas, but it operationalizes it totally differently. We didn't look at this fourth model. Actually, maybe the Greek's not useful. Let's just sort of talk about it in words. The fourth model says, let's look within kids. And let's say, let's let every kid have their own trajectory. Right? Let's do a kid-level fixed effect. And that way, in theory, we're going to eat up everything about kids that's time invariant. Right? And so we're going to say, same kid, right? But one of them we give, same kid on the same trajectory, one of them we give 8th grade algebra, the other one we give 8th grade general math. What happens between 5th grade and 8th grade that's special for the 8th grade algebra kid and the 8th grade general math kid? It's very much the same intuition as model 2. It's just economists will tend to like model 4. Ed psych people will tend to like model 2. They tell you the same thing. So with the exception of geometry, actually. But about 8th grade algebra, the estimate that we've got enough data on to really kind of cleanly estimate, they tell you the same thing, and that is that 8th grade algebra seems to increase kids' math achievement by about a 1/10 of the standard deviation. Okay, Let's skip that. Now, that's what happens on this general summary score of math achievement. But you're right to worry about ceiling effects on the summary measure. So let's ask, what happens in particular on the high-level skills that kids ought to be exposed to in 8th grade math, 8th grade geometry, and algebra courses? What happens to their achievement on those specific measures? Here I can't do a full panel analysis because on these high-level skills, the panel goes 0, 0, 0, 0, and then maybe 1. Right? Your predicted probability of being able to calculate the area of a circle is 0 throughout 5th grade because nobody knows how to do that, and hopefully it'll go up to 1 between 5th and 8th grade. So we do a slightly different model, but we've got 8th grade outcomes, and we're controlling for 5th grade scores. We're also controlling for kindergarten scores in some of these models, but that doesn't really matter. The main effect on the IRT scale is pretty similar. So this tells me this model is telling you sort of the same thing as the panel model. Here it's a 0.07 positive effect for 8th grade algebra on kids' overall Math IRT scores. But what's interesting is that the effects of 8th grade algebra of 8th grade math courses are focused in the sort of courses that are maybe most aligned with the skills that are measured. So you get a positive effect of taking pre-algebra on fractions, and you get a positive effect of taking 8th grade algebra on fractions, but it's smaller than the overall effect we observed. The big effect, on calculating rates, so on doing story problems. The bigger effect for 8th grade algebra you get is on fractions. You don't get an effect for pre-algebra on fractions, you don't get an effect for geometry on fractions, but you do get a big effect for geometry on area. So some of what this is telling you is that math classes work on the subjects that the math classes cover. But this is good news, right? Bad news, if you're inclined to be a pessimist, is that it also makes you worry that the positive effects associated with taking a fancy math class don't generalize, right? You put a kid into geometry, and they're going to learn geometry, but they may not, their arithmetic skills may flatline. This is a little disconcerting. I don't think this is the way we think about math learning, but it does seem to be the way the data are pointing. Another thing you can do with this analysis, but I'm not going to dwell on right now, is you can ask whether the effects of fancy math classes vary with kids' prior achievement. And let's just sort of suffice it to say for now that they seem to, but that's sort of exploratory, and I want to move on. So, okay. So from this first analysis, I take a conclusion that's pretty consistent with the prior literature, which is if you've got a kid and you want to decide what's best for that kid's math achievement, you're probably better off putting that kid into a fancier math class than a less fancy math class. Now, what we would want to do from a policy perspective then is to take all of the kids who aren't in fancy math classes and put them into fancy math classes. And in fact, that 0.1 standard deviation effect, if you do a little back of the envelope calculating, if you assume that it generalizes across the population, we can pretty easily eliminate our test score gap between us and the OECD if we can make that 0.1 standard deviation effect happen for every kid who's not in a fancy math class. So if we can get that effect for every kid, we ought to put every 8th grader into algebra and watch ourselves pass the OECD, leave them in the dust. California did this. California decided to do this over the course of a long time, over the course of a couple of generations. So let me give you a quick story about what happened in California. In 1987, and again in 1992, the California State Board of Education was reading Gene Oakes and said, we ought to make our goal. I really do think that they were reading Gene Oakes. I think that's what happened. They said, we ought to make it our goal to detrack, and we ought to do it in math. We ought to do it in middle school, because if we do it in middle school, it'll pass through high school, and we'll have a more equitable state. This was just at the level of words, sort of exhortations, in 82 and 92. But in 1997, the state starts to write content standards. It starts to write content standards for math, and starts to push in those standards the idea of getting 8th graders into algebra. Again, no real teeth here until 1999. In 1999, the state passes the PSAA. Let's see if we can get this, Public School Accountability Act. The PSAA is California's school accountability law. Right? This is the way in which California beat NCLB to the punch. And it creates incentives for schools to improve average levels of achievement. And built into the formula that schools are judged by in PSAA is a little boost, a little nudge for 8th grade algebra. If you enroll more kids in 8th grade algebra, even if they do a little bit less on the end of course test, schools get a little advantage. So schools now have an incentive under school accountability law to enroll more kids in 8th grade algebra. And in particular, low-performing schools have an incentive to enroll kids in 8th grade algebra. This is, the PSAA is passed in 1999. It's phased in over the next few years. We have good data starting in 2003 after it's already fully in effect. The state takes one more step in this direction in 2008. In which, when the State Board of Education says, okay, well, we've been giving you this little nudge to enroll more kids in 8th grade algebra, but let's get serious about this. And let's say that if a kid takes grade level math in 8th grade algebra, it doesn't matter how well they do on the end of course test, that kid's not proficient on state accountability standards. So it says to states, the phrasing was, algebra is now going to be the course of record for 8th graders. This is, if there's a little nudge in the PSAA, this is a push. This is about as close as the state can get to mandating 8th grade algebra for everybody. States, districts don't like it. They don't feel like they're well prepared. This is supposed to be fully implemented by 2010. They howl, there's a lawsuit. It never gets fully implemented, in part because of the courts, and in part because the state implements the Common Core, which is sort of agnostic on this 8th grade algebra question. So that's where we are. So, this policy history accounts for why California is enrolling far more 8th graders in algebra than any other state, literally any other state in the union. DC is at similar levels. And it also accounts for a nice steady rise in 8th grade algebra enrollment rates across the state, across the years for which we've gotten good district level data. So you see 2 bumps in this 8th grade algebra enrollment trend. So what I'm doing here, by the way, is I'm counting kids who take algebra CSTs, so they take the end of course test on the California state standards in algebra, or they take it in geometry. Those kids are counted as 8th grade algebra in these analyses. And what you see is that we go from about 40% in 2003-04 to about 60% in 9-10, with 2 sort of bumps statewide. One is at the beginning, as the PSAA incentives are finished being fully implemented. You go from 41 to 49 in that first year of this time series. And the second is between 2008 and 2009, when the State Board of Education says algebra for all, right? And again, you've got a 7-point bump in 8th grade algebra enrollment rates across the state. In this time period, the rest of, on a lot of other measures, the state's not changing a whole lot. Right? Demographically, percent of poor students is pretty constant, percent of minority students is pretty constant. Percent of English language learners is changing, it's declining. I think it's because of a push to get kids who are initially English, not English proficient, redesignated as English proficient. There's probably a paper there, but that's sort of for not thinking about it right now.
Just a quick question.
Yeah.
Why do you think that minority is always so much higher than the average proportion of kids who are in algebra are high? I mean, that's sort of surprising.
I'm sorry, so why is percent?
You're not saying that 61% of minorities...
No. This is just in the state, how many kids are black or Hispanic. Yeah, so I'm just saying, what I want to show you is that on sort of potential confounders, we're not changing so much. Okay, so statewide, if you look at it, at the broadest level, one more sort of little picky thing to tell you. I'm looking at about 300 districts in each of these years. Those are K through 12 districts. That's about 2/3 of the state's districts. Because in the analysis that I'm going to show you, I want to look at 8th grade algebra rates on Casey scores. So I can only look at districts for which I've got data on 8th graders and elementary school kids as well, and high school students. So those are the unified school districts. That's most kids in the state. It's not a big deal, but just so you know. Okay, so you got this sort of statewide trend. More kids taking 8th grade algebra. But what's interesting, and I learned this last summer when I was calling around to districts to try to get a team of districts ready to research this stuff at the district level. What you learn is when you bear down to the district level, you see huge heterogeneity in the way districts responded to this mandate from the state. So here I've got pictures. There's no reason why this doesn't have the names of these districts, but it doesn't, of 8th grade algebra enrollment rates for the 12 biggest districts in the state. Let me tell you, I wrote down here, LAUSD is 10. LAUSD's got a kind of an idiosyncratic story with 8th grade algebra. It gears up early before the mandate. You get the sense that maybe they panicked, like maybe they weren't quite ready to gear up, and so they scale back, and then they start to gear up again with the mandate. I've encountered other districts like this. In fact, I've encountered a district that has an even more dramatic story, where they went from 30% to 95%. Totally freaked out, fired their curriculum person, and went back down to 50%. That's not typical, but there really is no typical, right? There are several districts that are kind of flat, right? They're just sort of ignoring the state's mandate. Some of these are high-performing districts. Some of these are districts where they're just not worried about accountability. Maybe who knows? They're committed to differentiation, and they're not increasing their 8th grade algebra rates all that much, right? District 1, District 2, they're sort of slow and steady, but they're not doing a whole lot, right? There are other states that take big leaps, like District 4. Here's a district that got the memo when the state said 8th grade algebra for all, and exactly when the state said it, this district, District 4, went from about 50%, right? They're already acting in advance. They could see it coming, but they went from about 50% to almost 100%.
So what's the difference between District 4 and District 1 in their response?
Qualitatively, when you talk to them, this is a whole fascinating question. So I'm going to bloviate about this. I don't know in a really, I'm confident about this way. But when you talk to district people, you hear really different things. One thing you often hear is people who read DEOs. So you hear district people who say, this is our commitment to equity. We're going to get more kids into challenging math classes. And they've got a very strong commitment to it. You also, on the other hand, you'll talk to district people who, I mean, this is broad strokes, but who just sort of have a more technocratic approach. And they say, my teachers hate it when I send them kids who they don't think are ready.
Are you referring to top level sort of
yes.
These are sort of hunches that you have?
No, these are conversations that I have with district people.
Around top level district.
Curriculum people are the people I usually talk to.
Okay.
And so there are districts, you'll talk to districts who say, the state told us we ought to get more kids in 8th grade in algebra. My teachers hate it. My parents want us to do it, but my teachers hate the idea. So what we're going to do is we're going to have a test, and we're going to sort kids based on their performance on a test that they take before 8th grade. So they're just different approaches. And I think you can speculate that there are networks. You could expect.
I think that's actually really important.
Oh, I think it's fascinating.
Important question in playing out this data.
Yeah. So I'll tell you about what I'm going to do about this at the end. This is so nothing today. Hopefully in the future a little bit more.
This speaks about Andrew's work too, and I thought that you had said it, but
yeah.
if you think about the alternative incentive through NCLB, I'm wondering about some of these trends recently are kind of decreasing in the same time frame. The other incentive was to not put your kids in algebra because if you don't score enough on proficiency, then you get sanctioned. Right. So some of that falls at the school level rather than the district level. So this is Andrew McCacken, whom lots of you know, who's involved in this stuff, who helped me run some of these numbers. Andrew's got good evidence to show that API score drives 8th grade algebra enrollment rates at the school level. At the district level, you don't see that nearly as much. I can't quite explain why. But certainly, there low-performing districts have to pay more attention to, low-performing schools and probably low-performing districts have to pay more attention to this mandate, even though it's never fully enforced, because they've got more skin in the game. And so, when you think about District 12, those are people for whom the mandate might be starting to bite, right? And so they start to respond before the 8th grade algebra for all, because the API incentives are hurting them. So what you've got is a huge amount of heterogeneity. This is perplexing. It's a really fascinating question about policy implementation that I'd like to find a way to study. It's also a really nice opportunity for evaluation. Because
There aren't a lot of clear predictors for these different strategies. When you run a regression that asks, you know, who's pumping up 8th grade algebra enrollment rates and when, you see a secular trend, but you don't see a lot of other big predictors. It's kind of happening a little bit at sort of the big, from 50,000 feet, it looks kind of random. That's good for me. Because what I want to do in the analysis I'm going to show you today is I want to say, let's look at districts and let's ask what happens when a district enrolls more 8th graders in algebra to kids' odds of passing, actually to kids' math scores on the high school exit exam. There's one very good reason to look at, there are two good reasons, but let's say we'll go. There are two very good reasons to look at the high school exit exams that you found there. The first is every kid in California has to take the case in the spring of their 10th grade year. It doesn't matter whether they're on the algebra track or the calculus track, every kid takes the same test. This is the only test in math that every kid in the state takes at the same time. So that's, for matters of convenience, that's useful, that's nice. And the second thing is the Casey really matters, right? Kids have to pass this test in order to graduate high school. So they've got skin in the game. It's got high stakes for kids, which may mean that you get a little bit better data, but it just means it's an independently interesting and useful outcome measure, right? There's also a big problem with the Casey. And it's not so different from the problem we have with the ECLS-K test. And that is that the Casey is pegged to 7th and 8th grade state standards. It's a low skills test. It's a low bar, and it doesn't measure high level skills. The Casey, there actually is a ceiling when you look at the student level. So I can't look statewide because I don't have Andrew's data, but in the districts that I do have data for, you get about 10% of kids ceilinging out on the Casey. They can't do any, they literally cannot do better than they do on this test. It just is a little bit low. So that's going to undermeasure, it's arguably going to undermeasure the positive effects of 8th grade algebra. And I'm going to deal with that potential problem the same way I did in ECLS-K. The Casey reports subscales at the district level that represent the proportion of questions in different areas that kids pass. So I'm going to focus on the areas that seem to be most closely aligned with algebra and geometry and see whether you get effects of 8th grade algebra that are different on algebra and geometry than on lower level skills. So the intuition behind this model is, again, it's a panel model, very much like the model I gave you, where we've got districts that are observed repeatedly, right? Every district is observed from between 2004 and 2010, so you've got 7 observations for every district. Some districts come in and out because they're merged and so on, but basically you've got 7 observations for every district. And what you're asking is this change in X, in percent of algebra, right? How is that related to a change from year to year in Y, in Casey test rates? Controlling for the observable stuff, but most importantly, controlling for district fixed effects, right? The analysis is all within district, or it's sort of averaged across the within district analysis. This is a nice way to get around these sorts of problems of endogeneity, where the high-performing districts or the low-performing districts, or who knows what, are gearing up algebra at different times. The important thing to control for here is time, right? Because we know there are time trends on Casey scores, and we know there are time trends on 8th grade algebra. So that's a little bit tricky, but it's not that big a deal. Okay. So first, what do we see? What's the effect of 8th grade algebra enrollment rates on mean Casey scores? This is district level mean across these years. Here's where the news turns bad, right? When a district gears up, pushes more kids into 8th grade algebra from one year to the next, what you see is that average Casey math test scores fall. They fall by about as much as the positive effect for the individual level kid. So what happens at the kid level, the good news, the good positive effects associated with taking 8th grade algebra, the reverse happens at the district level. When you gear this up, when you make this a district policy, you see mean test scores fall. Really interesting when you look at the subscales. So Casey, let me read about this because I want to get it right. Casey has, the state reports 5 subscales for districts. And the subscales represent the proportion, the percent of questions that students in a district answer correctly in 5 different areas. The first is probability and statistics. These are questions that ask kids to interpret basic data displays. do things like calculate the mean or the median to represent a probability. These are pre-algebra skills, I'd say. Is that sound right to you, Morgan? They're the sorts of things you want kids to be able to do, right? It's applied math at a pre-algebra level. The second subscale is number sense. Here they're having kids deal with fractions, with percents, with ratios, scientific notation, calculating square roots. The third is algebra and function. I actually think about this as pre-algebra. This is generalize a pattern. Graph, look at a graph and try to figure out what's going on, what the pattern is here. Or look at a table and try to figure out what the pattern is here. Or solve a linear equation. This is very simple algebra. This is the sort of stuff that you probably did in 7th grade. Many of you, I'm assuming that you were sort of high achieving kids. The fourth is basic geometry. So this is convert between two measuring systems, or between coordinates to a shape, or calculate the area of a rectangle or the circumference of a circle. This is a little bit more advanced, right? And the last case he labels is algebra 1. This is deal with polynomials, or understand the difference between, understand what reciprocal means, or graph a linear function, understand what slope means, or solve an equation with two unknowns. So this is real algebra, right? So what do we see? What we see is that when districts put more kids into 8th grade algebra, they decrease average levels of student achievement on easy stuff, on the lower level math, and they don't do much to student achievement on the more advanced stuff. That's the overall pattern. These findings are super depressingly robust. You can do them a lot of different ways. You can control for this or that API or prior achievement. You can, gosh, we've done everything under the sun. The one place where we found a little bit of wiggliness in these is about how you count districts. When you count every district as one district, these results look a little bit better. When you weight districts by the number of kids who are enrolled in the district, these results look a lot worse. And what we've learned by sort of partitioning the sample and looking at it different ways is that the negative effects of 8th grade algebra, of a policy to increase 8th grade algebra, hit on big districts, but they don't hit on small districts. This isn't just LAUSD, unfortunately. It certainly hits on LAUSD. Take LAUSD out of the sample and the results look the same. But big districts look bad. Small districts looks like it's no big deal. It's sort of no effect. Okay. So, two analyses that tell you sort of two kind of puzzling things. The first is that for the individual kid, I'm reasonably convinced that it's a good thing to take a more advanced math class. 8th grade algebra is better than 8th grade general math for a given kid, right? I didn't dwell on this evidence. There's some evidence that this is a little bit conditional on kids' prior achievement. High achieving kids get more out of fancy math classes than low achieving kids. I'm not super duper convinced of this, but it's intuitive and it seems like it's in the data. But when you think about this from a general equilibrium perspective, when you think about it from a policy perspective, when on a big scale you increase 8th grade algebra enrollment rates, that seems to hurt student achievement, especially in big districts, maybe exclusively in big districts.
Can I just clarify something there? Doesn't that only mean because you're including new student scores that we wouldn't have otherwise, or like you're including scores of students that?
So the question, let's broaden your question. I think you've got a hypothesis about why. So the question is why.
Sorry.
And I think there are a few different hypotheses. Morgan's hypothesis is because when you put a lot of kids, a lot of low-achieving kids, I don't want to put words in your mouth. When you put a lot of low-achieving kids into algebra, there may be a tendency for teachers to not teach algebra content. So that what's called algebra stops looking like algebra. That's one hypothesis. We might be able to fix that, right? Another closely related hypothesis is about instruction and about the challenges to teaching heterogeneous classes, right? So Jim Rosenbaum had this sort of nice observation piece that he did a decade ago, where he went into a detracked high school, and he just listened to teachers talk about how hard it is to teach in Detract High School. They weren't well trained, right? And they didn't know whether to teach to the kid in the middle and lose the kids at the top and the bottom, or teach to the kids at the bottom, the top, and lose all the rest, and so on, right? And this is where things get very contentious, because there are lots of people who think they've got very good ways to teach in heterogeneous settings, but teachers aren't very well trained in them. So if it is a problem about teaching in heterogeneous settings, you might think there might be a solution. I think, if I understand you correctly, your hypothesis is different, which is the effects of a fancy math class are a function of how ready you are. And that could be. That finding that I'm not so convinced of, but I've got some indication, might be consistent with that. That's the most depressing finding of them all. Right? We can deal with teachers aren't teaching algebra. And we can even deal with teachers aren't teaching effectively to a broad distribution. But the readiness problem is a fundamental problem. And I don't have an answer. I don't know which of those three is the explanation. But I suspect that one of those three or some combination of those three is what's going on.
I have a question that piggybacks on that. The reason why I asked about the sequencing is I wonder when the state introduced this algebra for all, did they actually then take into consideration fixing all the other, the classes that come before that, so the kids are actually ready to take the algebra, rather than just dumping them in and just hoping that they'll sink or swim?
It's a very good question. I think the state would say yes, because the standards were being reformed and sort of streamlined toward 8th grade algebra. I know that when I've looked within individual districts, you often see 6th grade math test scores improving at the same time as 8th grade algebra is improving, which suggests that maybe something good's happening in elementary school to try to get kids into 8th grade algebra. But those 6th grade improvements hit a wall when you hit 8th grade algebra. So this is a question that's sort of hard to persuasively answer because I don't think we know what it means. The Common Core hopes to answer this question, right? It's going to streamline, whether it's effective. Morgan and I were just talking. Who knows whether or not that's going to work? But it's a good question.
To that point, actually, I think there was a lot of curriculum adoption that didn't happen in the late 2000s because 2008, 9, 10, 11, because of the budget crisis. And so the state dictated you have to adopt Algebra for all, and that you have to reform your standards, and reform the curriculum and the textbooks that you use. But then a lot of these little districts are also very poor, the large ones especially, and they got waivers from adopting the new curriculum. And some districts got waivers for years and years and years. So they may actually have had the revised standards, but then been using the same texts in all their math courses and their curriculum that they had not actually implemented, and that actually might have hit these larger districts more. I don't know the history.
Can I learn about these
you can probably back all the state board notes, which good luck, have fun. Which should be somewhere linked to the CDE website.
Okay, cool. Well, that's great. That's interesting. Okay. Yeah. So let me tell you. So I'm left with. In some ways, I'm left exactly where I started, right? Where I've got this evidence that something's good for kids and it's not good when it becomes policy, and I'm left with a ton of questions. With a couple minutes, I'm going to tell you what. No, actually, I'm over right now, so I won't tell you what I'm going to do, except to say that I've got a dozen or so partner districts that have agreed to do this sort of intensively, to share data and to talk with me about what they're doing over time, with the idea that hopefully, I'm going to skip. We can try to measure what's actually happening in the classroom. Measure instruction, and try to figure out whether there are strategies that work for intensifying middle school math better, so that this doesn't happen. So thanks. And I'm sorry to kill question time, but I'm happy to answer questions if you have things to get.
Sorry, did you say you don't have time?
I've got all the time in the world.
I was gonna say, I come from a special ed background, so my concern always is that really there are sometimes students that are just not ready for moving forward. And have you had have these districts faced a lot of pushback from people like me?
Yeah. So this is it's a really politically, this is a fascinating question, right? Because on the one hand, there's an equity push. Which I think leads you to want to get more kids into 8th grade algebra. And on the other hand, there's special ed people. So I was so excited about this because I come from this sort of my background is like detrack, right? I was so excited, and then you talk to people who say this is evil, right? This is so mean because there are kids who aren't ready, and if you're not going to accommodate them, differentiation happens, which is it makes all the sense in the world, and it wasn't at all in my mind. And you see, when you talk in districts, and particularly at the school level, you do see a lot of pushback. And so this is part of why I think there's so much heterogeneity between districts, because which of these voices is sort of in power, and the extent to which it has power, I think explains a decent part of that difference between districts. I'm speaking beyond my data right now. I've talked to a dozen districts, and I've talked to a few people in a dozen districts. But yeah. Teachers in general don't, my sense is, this is a cocktail talk, right? Cocktail party talk. When I talk to middle school math teachers, again, over drinks, they'll tell me that they don't like eighth grade algebra for exactly the reasons that you're suggesting.
But then I'm just left with something that you said earlier. How much of it is that the teachers are not trained to teach the students the way that they need to learn?
Yeah. Well, there are literally math wars about this, right? I mean, that's not literally, thankfully, but yeah. So Joe Bowler and a lot of other people in math education would tell you that. In fact, some of these people have told me this work that I'm doing is kind of stupid because, of course, it didn't work because the teachers weren't trained. My answer to that, I think that's actually kind of. I think that's a. I'm not sure that we know all that well about teacher training and about the strategies that work. But I do think this is the way it was done in the real world, and so it's worth sort of wondering about that. But it's certainly it's my fervent desire, both because I care about these outcomes, but also because I'm going to be better off professionally if I can find a district that did this really well, right? And they've got the secret sauce, and it may very well be training teachers to teach heterogeneous students effectively. I hope that that's true.
Thank you very much.
Okay.